Hi, how's it going? I'm Gavin Wolfe, and I'll be teaching you guys how to do Chapter 14, Section 2, which is double integrals. So as many of you know, we discussed integrals in Calculus 2. They were used for all different sorts of means and procedures to find volume and area under a graph and whatnot, and they come back up here in Calc 3, and they're used to find many more important topics, including that of volume, line integrals, surface integrals. You really can find a lot of different important mathematical topics, and double integrals and triple integrals are all a part of them. So let's hop right in. So in order to start a double integral, it always involves a setup. You have your limits of integration, you have your function that you're integrating, and then you have your dx and your dy. And one of the more important things that you need to have is you need to remember that when you have your dx value right here, right, you're integrating with respect to x values only. Once you integrate that, it's like doing a single integral, then you can go ahead and move on to your dy's, right? And this is for anything. If it's a dr or d theta, you start from the inside and then you move out. And you work that integral with only the values that correspond to that dx, right? So you can't integrate your y's with your dx. You can only integrate your dx's with your x's. So we're going to start with this one. We're going to integrate along x, so then it's going to be 32 x to the fourth over 4 times y to the third, integrated upon -1 to 2, and we have this integral still standing right here from -2 to 1, and then dx dy. So now that we've gotten here, we're going to just basically keep that y value as basically a constant that is multiplied to it, right? So think of any other variable besides the one that you're integrating upon as just a nice constant that basically doesn't really bother the main value that you're integrating. So in this case, 32 divided by 4 turns into 8x to the fourth times y to the third. And then we're going to integrate that from -1 to 2, right? And so this is end up equaling, we need to get rid of this because this is always integrated. So you have dy, -2 to 1. Okay, so now we're going to move this way, and we're going to say, okay, you're going to write your first value, 8 times 2 to the fourth, y to the third. We're going to actually factor this y to the third out. So we're going to do 8 times 2 to the fourth minus 8 times -1 to the fourth, right? Okay, and so basically, now that you have your y out here, by the way, we're going to go ahead and solve this in here. So then that's just going to be 8, right? And this is going to be 16 times 8, which is going to be, let's figure that out real quick. Okay, 16 times 8 is, hold on, my calculator just died, and I have to use this beautiful computer here. So 16 times 8 is going to come out as 128. Okay, sorry about that. I don't know why that took that long, but whatever. So 128 minus 8 right here is going to just leave you with 120. So now we're going to bring it down right here. You're going to have -2 to 1 of y to the third times 120, right? You already plugged in your x's, right? And so then basically dy, right? And so then we're going to integrate upon y. So you're just going to be, or it's going to be y to the fourth over 4, that, times 120. 120 divided by 4 is equal to 30. 30 y to the fourth. And we're going to integrate that upon -2 and 1, limits of integration. So 30 minus, let's see, -2 to the fourth. So that's 30 times 16. That's going to be your final answer. So you basically just did your first double integral, which, great job. We got through the first one. Now we get to move on to the second one, which itself is seemingly harder, but not as bad as people like to put it out to be. So basically, we're going to start out with this integral right here. And as we can see, we have a variable in the no longer constant in the limit of integration. So we do have to approach this a little differently, but here's a way thinking of it. When you're looking at graphs and you end up having to take double integrals to find area and to find volume, you need to remember that this outside integral should always be constants, and then the second inside integral or the third inside integral, which if you're taking a triple integral, can conclude constants, and it can include variables. So we don't want to see a variable on this outside integral, because then you can't really integrate it, because you're basically plugging in those variables after you don't get a number, right? So basically what we're going to start with, though, is the idea of, let's go ahead and basically start with the dy's, right? So 6x squared plus y, that ends up turning into 6x squared times y, because when you integrate, that's supposed to be a constant, you add a y to it. And then we're going to do plus 2y squared over 2, which just turns into y squared, right? And so now you can integrate that from x squared to 4 dx negative 2 to 2, right? And so basically, you just have to approach these as something where you move from the outer integral to the inner integral, right? I mean, when you go from the inner integral to the outer integral, and it's the same way this. You always move inside, out. And that's going to be very important, as you'll see, as many of the double integral problems that you come across will end up being something along the lines of you having to integrate either variables, you might have to integrate among multiple functions, right, to where they go in your limits of integration, which is very fun. But you need to remember that you always should be ending off with some sort of constants, because realistically, that's what's going to not leave you with a variable in your answer. So once we go from here, we can plug in some of our limits of integration. So we just did y values. So if we plug in 6x squared times 4 plus 4 squared, right? That's one of them. And then minus 6x squared times x squared, right? Plus x squared squared, right? So now let's simplify this out. We're going to get 24x squared plus 16 minus 6x to the 4th, and then plus x to the 4th, which that just turns into 7x to the 4th. So 24x squared plus 16 minus, well, that's actually a negative, so it's going to turn into 5x to the 4th. Well, wait, hold on a second. Maybe I did that wrong. Shit. Okay. Yeah, you're right. It is negative. It is 7, because when you distribute that negative, so it's a 7x to the 4th. Okay, and so now we're going to do dx, and we're going to have this interval right here. Probably should have written all of these. Okay, so now we can take the integral of this, which is going to be more fun. 24x to the cubed over 3 plus 16x minus 7x to the 5th over 5, evaluated from negative 2 to 2. Okay, so if we look at this is going to be a fun integral, but we're still going to finish it, right? And so the idea is, if we take 24x cubed over 3 plus 16x, right? We plug in that 2, so 24 times 8 over 3 plus 16 times 2 minus 7 times 2 to the 5th, which ends up being a fun number. I know 2 to the 4th is going to be 16, so that's going to be 32. So, yeah, and then you're going to, this is one value, and then you're going to subtract that all from another value of negative 2, which is going to be fun to do too. Plus 16 times negative 3 minus 7 times negative 3 to the 5th over 5. Okay, so now that we've gotten here, I think it's a good place to basically stop, because at this point it's just simplifying an integral in I think that is a waste of time. I would rather go ahead, and now that we have looked at this across the board, there's one other thing I wanted to add in, and it is a simple idea of integration. So, for example, if you had an integral of something like, you know, -1 to 1, and let's say that it was from 0 to square root of 1 minus y squared, for example, right? And then you had a function like x squared plus y squared, and then you had dy dx. So there's something important to remember about this. Oh, dx dy, because that's okay. So there's something to remember about this, and I just want to touch up on this quickly, is you need to convert sometimes your limits of integration. So you could solve this out by doing the derivative, or the integral of it. It's not very nice though, right? A better way to do it, and you're gonna have to do this often with rectangular form, is what you're gonna want to do is you're gonna want to say, okay, we know that r squared is equal to x squared plus y squared for rectangular coordinates, right? So let's go ahead and sub that into there, and then let's change our limits of integration around. So what would be x squared plus y squared, right? Well, an example of that would be, well, okay, so here's one thing that we need to remember. If this is x squared plus y squared, for example, right? We need to remember that actually equals a circle, right? And so if that ends equaling a circle, right, one of the things that you could do is you could say, okay, you would want to integrate along where you would just say dr and d theta, right? But you don't have a d theta in this one, so it wouldn't be a good way to do it. But what I'm trying to say is, in this case, it actually would work out better, now that I look at it, to go ahead and do it with this kind of integral. But if you change this, right? Okay, so you say this actually x squared plus y squared, right? You would want to change this if this is r squared is equal to x squared plus y squared, right? That's also equal to r sine theta, right? And then dr, right? Well, actually, instead of it being like that, it would be, so if you did this, right, it would be sine of r squared dr d theta. And then you got to change your limits around, which is fun, which you would do. Negative pi over 2 to pi over 2, because what is sine equals -1 and 1, which is negative pi over 2 and pi over 2. You go 0, and then you could say, oh, okay, for this one, it's still going to be 0 to 1, just because if you go ahead and see where the radius r, right, because we're integrating along dr, the length of r is always going to be 1 in this case, because it's x squared plus y squared, which is equal to a circle, right? And a circle always has a radius of 1. So I hope that's not too confusing, but that's basically to finish it up. You're going to have to sometimes convert into rectangular form. I know this was kind of messy, but the idea is in this case, if you, and I didn't have the sign in the beginning, but if you have the sign there, the only way to integrate that is you're really going to want to convert that to rectangular form. So that's the idea. I hope you guys enjoyed. That's 14.2. Thank you for watching. Gavin Wolfe signing out.